Good morning from Singapore. My name is Dr. Stephen Wong, and I welcome you to the third and final Imaging Informatics in Asia session. This is session 3022. I hope you have enjoyed the previous two sessions. Today's speakers and your topics are as listed. Dr. Justi Anthony Chiramo is the clinical advisor at Cure AI. She graduated from the Christian Medical College in Bangalore, India, and worked as a consultant physician in Bangalore before joining St. John's Research Institute in 2015. She is a member of the Digital Health India Association, which is a non-profit organization that works towards enabling digital transformation of healthcare in India. Our next speaker is Professor Akira Kunimatsu from International University of Health and Welfare Mita Hospital, Tokyo, Japan. He has written multiple publications in AI and neuroradiology. The next speaker is a good friend of mine, Dr. Tian E. Lian, who is a senior consultant radiologist at the National University Hospital in Singapore. Lian has been involved in several AI projects and in his department, some of which he has implemented. And our last and final speaker for the Imaging Informatics in Asia series is Dr. Vida Mahajan from Mahajan Imaging, New Delhi. He did his MBBS medicine in Mumbai, India, and internship in Mumbai and New Delhi before joining Mahajan Imaging, where he was involved in business expansion and information management systems. He is also the head of research and development at Caring Institute Research in New Delhi, working on CARB AI, which is an end-to-end testing and deployment platform for medical imaging AI. My fellow chair is Dr. Ravi Shrestha from Canon Medical Systems Corporation. Thank you. I hope you enjoyed today's session, and do come back and join us for the next session in SIIM 2022.
Hi, good evening, everyone. I'm Justi Anthony Chiramo. I'm an internal medicine and tropical medicine consultant based out of Bangalore in India. I work as a clinical advisor for Cure.ai, and we are very grateful for this opportunity for us to speak about our experiences and challenges in deploying AI-based radiology solutions in rural India. Today, I'll be running through these topics. I would like to set context in the beginning before I speak about our work. So just to give the context of Indian healthcare system, this is WHO's slide, which shows how many doctors are there per 10,000 population. And you can see the darker it gets, they have higher density of doctors. So you can see, for comparison, I've taken a few countries out, like Europe has, some of the countries have the highest density with 80 doctors per 10,000 population, and it gets lower when it comes to India to less than 10, and some of the countries in Africa is even less than 1. And to look at the basic requirement of having 1 doctor for 1,000 population, only 9 to 10 states out of the whole of India fulfills that requirement. That means 70 to 80% of the population don't live in places with this kind of a luxury. We are based out of Mumbai. Our group is called Cure.ai. It was founded by Dr. Pooja Rao, who is a clinician herself, and Dr. Prashant Warrior, who's a data scientist. And over the past 5 years, I've had a very fulfilling journey with them. And these are some of the achievements we've had. The Lancet's first AI publication in radiology is from our team. We recently got WHO endorsement for mass screening for tuberculosis. And thanks to this New York Times article that featured our work in rural India, that I got this opportunity through Dr. Steve Wong to present here. So this is over the past 5 years, we've developed a few products, but talking about our chest X-ray software. It's called QXR. I'll just tell you briefly so that you understand what it is, what it entails, and how it was used in rural India. It'll be more clear. So just to show you how this X-ray software, what this X-ray software is about. It is trained on 4 million chest X-rays with their corresponding radiologist report. It can detect 29 abnormalities, including lung, pleural, or cardiac findings. It can work on analog X-rays as well as CR and DR systems. You can see how an X-ray is being captured and how the report is being accessed, and all the reporting happens within a few seconds to a minute. We also, our focus disease areas, it can give a screening for COVID-19, TB, or other global health issues. COVID risk is usually stratified this way as no risk, low, medium, and high risk. Now, this also, our software can also look at sequential X-rays and quantify the percentage of lung involvement, and that can be figured in a table or in a graph way, which can be customized. And that also helps doctors who are managing COVID wards to see if their patients are getting better or worse. So this software was, we are happy to say that it was deployed in some of the dense suburbs in Mumbai, with the partnership in partnership with the Municipal Corporation of Mumbai, and organizations like PATH and India Health Fund were already working on TB with us. So what we did was we loaded our software in the portable X-ray machine, which was loaded onto a bus, and that was taken to the slums, and where patients, as you can see, not patients, actually they are asymptomatic people who are living in the communities. They were screened using an X-ray, and their vitals, and the reports were immediately looked at on the laptop or on the phone, and they were able to make triage decisions to do RT-PCR testing. And this was particularly effective and has been particularly effective because RT-PCR test kits are sometimes we run out of most of the times. This actually gave us a lot of credibility, and we were able to get funding from Gates Foundation and Dell Foundation, and we decided to scale it up. For that, we looked at this set of hospitals, which are the rural mission hospitals, who are doing cutting edge, exemplary healthcare work in the most remote parts of our country. And they are kind of like secondary level hospitals that cater to 2 to 3 million population. And there, they have like one doctor for 100,000 to 200,000 population. And that's the kind of doctor population ratio we are seeing there. And definitely there are no specialists, no radiologists, no RT-PCR testing. When we approached them, the doctors were more than happy because there they do on multiple hats, as in the physician doubles up as cardiologist, neurologist, nephrologist, pulmonologist, etc. Same thing, surgeon doubles up as obstetrician or gynecologist. So for them, this technology, they realize it's going to help them a lot, and they've embraced it immediately. And the deployment process was extremely smooth because they didn't have to buy any additional hardware, just the basic Windows 7 laptop or computer, which could also be a receptionist computer, but all that is what is required for this deployment. Basic IT expertise, minimum internet speed of 4 Mbps, and the whole deployment was done remotely, and maximum of 2 hours. Also, additionally, we took half an hour to 1 hour to train the radiology technicians and medical staff. And we are proud to show you that we've deployed in 20 such rural mission hospitals across 14 states in India, which are marked in green. We've processed more than 25,000 chest X-rays so far. This is from last September. And you can see we actually got additional funding, and we were able to scale it up from January. That's why the number of X-rays have gone up. Now we process around 4,000 to 5,000, close to 5,000 chest X-rays a month. And what this slide I wanted to show is, as a breakup, this is only from a small data set, what we could collect the data because of the lack of manpower. They are not able to do data collection to the extent we needed. But in that limited data set, we found that 46% of the X-rays were labeled as no COVID, and 54% had COVID risk given as low, medium, or high. We wanted to specifically show that 11.2% of the patients were underwent chest X-ray not for COVID as a COVID suspect. Their X-rays were taken for something else. It would have been preoperative screening, or it would have been an RTA followed chest X-ray. So, but these were incidentally picked up, and that was because of our software that they were able to look for COVID in these patients. So how did it help? How has it been helping healthcare workers in quick decisions? Because usually the doctors wait for the patients to come back. Till then, nobody looks at the X-ray. Here, we are able to give them access to the report and the X-ray on their phone in less than a minute. Safety, because they were able to now isolate patients who were found to have some kind of a risk of COVID. For patients, it meant early triage for testing, as well as disease progression monitoring if they were admitted. For the community, it meant that we were able to pick up, at least to a certain extent, some of the asymptomatic cases, and thus help reduce transmission. Just to stress on safety aspect, there were a few hospitals that were shut down last year for 2 to 3 weeks because a lot of their staff had fallen sick with COVID. And they have well received, all these hospitals have actually received this technology. And we have a blog about this. The link is given in this slide. We do face a lot of challenges. One of the main things that network issues. I did say basic internet speed of 4 Mbps is required, but that also is difficult in these remote areas of India. Choked healthcare resources. We've been actually trying to scale up thanks to the funding, but unfortunately, these hospitals are really overworked, especially with the pandemic, that we're not able to actually even have a conversation with them to go ahead with the deployment. There is, of course, a small subset who showed a fear in trying out new technology. And we do face this issue of, because we're not able to validate, because we don't have the test results, and there is lack of resources when it comes to trying to get data to correlate the validation process. So we went a step ahead, and we realized how the hospitals are functioning. So we realized our CT Brain software could be of value in the emergency rooms there. Our CT Brain software can pick up 12 different abnormalities, critical abnormalities like bleeds, infarcts, mass effect, midline shift. It is FDA approved, and all these report happens within 1 to 2 minutes of the CT being done. And we are also able to notify the clinician in the emergency room via WhatsApp or Telegram. We are able to notify along with the report as well as the key slices so that they can make the decision faster. So this is a success story from Tezpur, a small village in Assam, which is in the foothills of Himalayas, where we were able to help them out with this CT Brain software, especially in cases of stroke, where they were able to make thrombolysis or thrombectomy decisions early, or referral in cases of severe head trauma. They were able to do that. Earlier, they were dependent on teleradiology setups, which would take 15 minutes in critical cases, up to an hour for them to get the report. Whereas here, they were being notified in 1 to 2 minutes of the CT being done. Again, we've written a blog about it, and you can access it through this slide. So what is the potential for AI in global health? This is an important slide. This is not mine, courtesy to Simon Harris. Always AI has been portrayed as an assistance to a radiologist or augmenting radiologist workflow. But you can see where the radiologists are densely placed in the most developed parts of the world. 85% of the globe don't have this luxury. And my takeaway is this, that AI augmenting a non-specialist physician model definitely needs acceleration. And it's not something of the future. We can actually do it. It's happening now, even in the resource limited settings. So this is my takeaway. I'm really grateful for this opportunity again. Please feel free to ask any questions if you have any clarifications, and feel free to reach out to get more details as well. Thank you very much.
Thank you for inviting me to this session. It is a great honor to be here today. First, let me introduce myself. I'm a radiologist at a university hospital, and my area of expertise is neuroradiology, especially MRI. In the next 10 minutes or so, I'm going to talk about AI and radiomics research led by radiologists in Japan. And then I'd like to mention some of our past research. I have nothing to disclose. Over the past few years, there has been an explosive increase in the number of publications on AI and radiomics in PubMed. Last year, the number of papers published per year reached 3,000, and this year, it will surely exceed that number. There is a similar upward trend in papers originating from Japan, representing about 5% of global total. Most radiologists in Japan specialize in clinical practice. They spend most of their working time providing clinical services to their patients, and they have no or little experience in computer science and programming. Their departments have no or very few computer scientists nearby. However, they have access to a very large number of medical images stored in the hospital PACS system. In contrast, computer scientists have very high computer skills compared to medical doctors. They can devote much of their working time to writing code and fixing bugs. However, it is rare to have a doctor working near them. Also, they rarely have access to medical images except in public repositories. In addition, it is often difficult for them to point out that there are abnormal findings on images. As I mentioned earlier, until just a few years ago, the majority of radiologists in Japan had no or very limited experience in computer programming. Of course, some radiologists love computers since childhood and are highly skilled, but they are very rare. However, when AI started to show high performance in image classification, some radiologists started to try it on CT or MR images in their hospitals. They read how to add code on the web, downloaded the Python sample code from GitHub, made a few edits to the code, and fed the image data to the model. AI and radiomics research by radiologists in Japan has often started with such self-efforts of these motivated radiologists. The pie chart below shows the breakdown of papers from Japan on the topic of deep learning or machine learning for CT and MRI. The most common topic is detection, followed by image classification, segmentation, and image reconstruction. In the next half of my talk, I will present some of our papers on AI and radiomics. The first one is a paper by my colleague Dr. Yasaka. Japan used to have a large number of patients with viral hepatitis. It is still important for us to diagnose liver lesions with CT and MRI scans. So we developed a deep learning model for differential diagnosis of hepatic masses based on CT images. More than 1,000 images of hepatic masses were used for supervised running of CNN with the structure shown below. Using this model, we were able to differentiate between benign and malignant hepatomas with an accuracy of 84% and an AUC values of 0.92. The next topic is on the staging of liver cirrhosis. Liver cirrhosis is the end stage of chronic liver disease. It is clinically important. Liver biopsy is the standard method for staging fibrosis, but it has risks of sampling errors and complications. It is possible to assess the degree of fibrosis based on imaging, but it may be subjective and diagnosis of early fibrosis is often difficult. We developed a deep learning model for the staging of liver fibrosis using contrast-enhanced MRI. Using more than 500 case images and staging results, we performed supervised running of CNN shown here. The relationship between the scores obtained from the trained model and his pathological fibrosis stage is shown in the graph here. A significant correlation was found. The following paper is the work of my colleague Dr. Akai. In terms of hepatocellular carcinoma, due to the high recurrence rate after resection, it is clinically important to predict the risk of tumor recurrence and prognosis before resection. The motivation for our study was to predict the prognosis of patients with hepatocellular carcinoma using CT images alone. We showed that the random forest classifiers could distinguish between low and high-risk groups in terms of survival. For descriptive features such as demographic, biochemical, and pathological data, only the presence of venous invasion was predictive of survival, but it was less reliable than radiomic features. Our next topic is on Parkinsonian disorders. Parkinson's disease is a brain disorder that leads to shaking, stiffness, and difficulty with walking, balance, and coordination. In addition to Parkinson's disease, several other diseases show Parkinson's symptoms, such as progressive nuclear palsy and multiple system atrophy. The problem is that the standard treatments and the rate of progression vary completely from disease to disease. A total of 356 patients were enrolled in the training and was validated using 63 patients. The deep learning model achieved high accuracy in the differential diagnosis. The AUC value was also high and was over 0.9. Our last topic is my past work on the differentiation between brain tumors with MR-based radiomics. Here you can see contrast-enhanced MR images of glioblastoma on the left, lymphoma on the right. As you may know, these tumors sometimes look very similar, but the problem is that the standard treatments are completely different. We developed machine learning models to differentiate them. Methods are shown here. The results of cross-validation are on the left, and the results of testing are on the right. Finally, I will discuss the future of AI and radiomics research in Japan and the challenges we are facing. The standardization of methods is expected to progress in line with the global trend. The shift from single-center studies to multi-center studies is inevitable. As a result, image data sharing is becoming increasingly important, but the running cost of data sharing, such as hardware and labor costs, will be an issue. There are more and more collaborations between radiologists and computer or data scientists, I hope. However, several issues need to be resolved. The current Japanese law on clinical research does not allow corporate profit-making activities within the research. Therefore, the image data collected can't be used for anything other than research. And also, even when handling anonymized medical data based on the Personal Information Protection Law, it is necessary to obtain separate consent from the individuals. Because of these regulations, it is difficult for companies to enter the medical image AI market in Japan. This is the summary slide. AI and radiomics research has been increasing in Japan. Radiologists rigorously participate in such research. Standardization and research quality improvement are upcoming issues also in Japan. Improved reproducibility will accelerate the use of AI and radiomics in clinical practice. Great thanks to my colleagues and thank you for your time.
Hi, good evening and greetings from Singapore. My name is Yi Liang and I'm a radiologist. So during the COVID pandemic last year, when the majority of us were working from home, there was a lot of time for me to actually do something I've wanted to do for a long time, which is to actually learn the coding and the more practical aspects of deep learning. Now, prior to this, I was working with data scientists on a few algorithms such as pneumothorax detection and fracture detection, but I felt that I didn't really appreciate the practical aspects. And so last year was a golden opportunity for me to pick up the coding and to implement my own networks. So today I'll share with you the things I learned along the journey, some of the myths about learning coding for deep learning, and how you may want to do the same if you want to actually get started on training your own neural networks and implementing your own AI algorithms. It's actually so easy to get started on neural networks nowadays that within 6 months, I was able to program this network for pneumothorax detection with the corresponding heat map. This was a prostate whole gland segmentation algorithm I did. And this was a natural language processing algorithm, or NLP, which classified X-ray reports according to the presence of a fracture. So the biggest hurdle to learning to program your deep learning networks is really to learn programming at all. Most people will say, I don't know any programming, it's just too difficult for me. So myth number one I want to dispel is that you need to know lots of computer programming to even do any deep learning. Now, I have to admit that you have to know some programming to do deep learning, but I started with zero programming experience, so it's completely possible. Now, the most commonly used data science programming language by far is Python. And the great thing about Python is it's designed to be an extremely readable, very natural kind of language, so that even when you just look at the code, you can pretty much get a sense of what is going on. So it's easy to learn, yet it's extremely versatile. So whatever coding or programming you pick up from your deep learning experience, you can actually apply to a lot of other things just to automate a lot of tasks that you never knew you could automate. And it's the fastest growing programming language right now. So if you have any incentive at all to learn programming, you really should pick up Python. So the step one to do your own deep learning network is really to learn some Python. It's just a lot like learning a new language, whether it's Chinese or Spanish or Italian. All right, so I suggest giving yourself about a month for this, all right, or roughly about 20 hours, and probably a lot less if you ever had any kind of programming experience. Now, the objective of this month is not to completely master Python. It's almost impossible, okay, but you just need to know enough syntax or grammar just to move forward on your deep learning journey. Now, there are a plethora of options to learn Python nowadays. There are books if you're still use a traditional style, but there are tons of free YouTube videos as well as online courses where can really get you started very, very quickly. Now, during this phase of learning Python, motivation is really key. I have to admit, I got started on learning Python and stopped at least 3 times before I cleared this hurdle. So my suggestion is to pick a short book and to be involved in projects or write short scripts that teach you more about the language on little projects that you actually like to do. For example, an automation script to rename all your picture files in a certain way, or an anonymization script for DICOM files, for example. Now, if you like to program games like Space Invaders and that's your kind of thing, that's fine too. You just really want to pick up the syntax during this phase before you move forward on the rest of your deep learning journey. The other tip I would give is to use Jupyter notebooks. And I don't mean the planet Jupyter, okay, but this Jupyter, which is basically a web-based editor or interactive programming kind of interface that allows you to combine text, code, and visualizations all in one document. It's really good for inexperienced programmers like most radiologists would be. So it basically allows you to code, you execute the code, and see the results instantly. And later on, when you get into deep learning algorithms, it's great for data visualization and just for experimenting with bits and pieces of your code. So step 2, after learning some basic Python, is to learn a few essential Python libraries for data science. Now, what is a Python library? A library is basically a collection of commands written in Python just to make your life a little bit easier. So the libraries we deal with in data science are NumPy, which are for advanced math and science calculation, Pandas, which is a bit like a programmer's version of an Excel or spreadsheet, and scikit-learn, which provides some very basic kind of data processing and data manipulation techniques. Which brings me to another myth which I want to dispel, and that is that you need to know very advanced math theory like advanced calculus or computer science in order to do deep learning. Now, you need to know a little bit of math, all right, maybe some basic algebra, basic matrix multiplication, and some very, very basic calculus, like, for example, that the gradient of a slope is the differential of the equation. But beyond that, you don't really need to know advanced math in order to do application of deep learning. Now, if you want to write a brand new algorithm from scratch, or you want to go into the really technical side of things, then you need advanced math. But certainly in order to apply deep learning and AI techniques to our domain, which is radiology, minimal math is needed for understanding what's happening under the hood. So step 3 is to learn a deep learning framework. Now, what is a framework? A framework is basically a collection of libraries that you can use for data science or deep learning. So the 2 major deep learning frameworks today are TensorFlow Keras, which is supported by Google, and PyTorch, which is supported by Facebook. Now, I don't suggest you pick the deep learning framework based on whether you prefer Google or Facebook. In fact, if you're a beginner and you're just getting warmed up on your Python code, just start with TensorFlow Keras, because Keras is a lot easier to manage, the code is a lot less verbose, and it's just all around suitable for beginners. And when you do your first few deep learning projects, start with simple classifiers. For example, on small data sets like cats and dogs, which are open source, and you can download these images from kaggle.com or many other kind of websites. Start with simple projects like that before you start working on an algorithm for segmentation of 3D MR images for multiple sclerosis, for instance. So how do you get started on learning a deep learning framework? Well, it's a bit like learning Python, and there are plenty of books, videos, and online courses out there. Too many options to choose from. What I did was to start with a book. Highly recommend this book called Deep Learning for Computer Vision with Python by Dr. Adrian Rosebrock. This is a very, very practical-oriented book, especially suited for beginners who are just starting out on their first few deep learning projects. And really, it takes you from most basic kind of neural network and all the way to the more advanced kind of deep learning projects you might want to do. Another book I strongly recommend is Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And this book covers both practical as well as a lot of theoretical aspects. So as you move along your deep learning journey, you'll find that you need to know a bit of the practical as well as the theory at the same time, and they must kind of keep pace with each other as well. And of course, the Kaggle data science website has plenty of well-commented code for beginners. And what I find is it's very useful to actually just type out the code letter by letter rather than do copy and paste, especially if you're doing it from a website or from an electronic book, for example. Just the effort of typing out the code somehow ingrains a lot of the commands for you. And now it brings me to another myth, and that is that you need a lot of money or resources, or you need some kind of supercomputer to do deep learning. Now, you definitely don't need any of that stuff at the start. First off, all the software that I've described so far, the Python codes, the deep learning frameworks, these are all open source, which means they are basically free. And state-of-the-art algorithms are actually released by universities as well as the top deep learning researchers from Google and Facebook. And guess what? Most of what Google and Facebook releases is free. And you definitely do find just using state-of-the-art algorithms that these big companies have released. Which brings me to hardware. Do you need a supercomputer to do deep learning? At the start, you definitely do not. Whatever you have on your desktop computer is definitely more than sufficient. You can even use your laptop to get started with most of the initial deep learning projects. And when you are advanced enough and you want to start working on bigger and more complicated data sets like radiology images, then you'll probably need to buy a graphics processing unit. And that is basically the kind of computer gaming card that you use to play computer games, or your children use to play computer games. And you can definitely get these for almost a few $100s on eBay. And that is enough to take you pretty far away. And if you want to progress even beyond that, then maybe it's time to start writing a grant to get some GPUs. But for a start, there's definitely no need to get any kind of supercomputing resource. And how about data? Even though we all work in medical or radiology departments, it's surprisingly difficult to get to the DICOM data nowadays with all the privacy protections. So I really suggest when you first start working with radiology data, you start with open source radiology data. And there's plenty out there in the native DICOM format, and it really gives you a feel for working with radiology images and the kind of DICOM format and just playing around with that. And then when you're ready to go, then you can start extracting your own hospital's DICOM data for research. And I think many of you know this already, but really Google is your friend when it comes to just finding out anything that you want to know. And in particular, if you run into bugs, and you definitely run into bugs and error messages as you go along, just cut and paste the entire error message into the Google search bar, and it will normally direct you to a website like Stack Overflow, where you'll be surprised about 10 other people have already asked your question, and there are about 20 different answers to what you need to know. So almost every single error message or bug I've gotten, I didn't need to call or ask the programmer. I would just enter the error message into the Google search engine, and the answer will pop out in 1 or 2 clicks. And as I've already mentioned, Kaggle.com is a great data science competition website, which is an important resource. They have a few radiology-focused competitions that have been sponsored by the RSNA, and there's plenty of clean DICOM data and code to get you started. And by the way, Kaggle.com is also owned by Google. And despite all this, all the books, Google, all the error messages, all the support you have, inevitably you run into a brick wall. And what I mean by brick wall is when no matter what you do, the program just keeps returning an error message, they're out of memory, or they can, a bug here, and you just cannot fix it, no matter how much effort you've put into it. When that happens, I suggest just take a break from the coding for 1 or 2 days, and then you get back at it. And then when you have a fresh look, somehow the solution comes out more easily. And then you Google again, and hey, the solution has been there all the time. And there'll be many of these brick walls and moments when you definitely feel like giving up. But don't worry, it's all part of the journey. Just take a break for a little bit, not too long, and then get back to it 1 to 2 days later. And you'll be surprised how much you can overcome that way. So to conclude, my own personal journey of learning deep learning and data science was just really fun, and I'm definitely not done with it yet. I think that the barriers for radiologists learning about deep learning are reducing every single month, and I would definitely encourage many of you to just try it out as well. And if you have any questions, feel free to contact me at this email, and then we can get in touch, and I'll be happy to answer any questions as well. Thank you.
Hi everyone. I'm extremely grateful to the organizers of SIIM for allowing me the opportunity to talk about some of our work. My name is Vidur Mahajan, and I'll be talking about pre-deployment testing as it pertains specifically to medical imaging AI. Now, why is pre-deployment testing important, and why pre-deployment, and why don't we call it validation? So, the first and foremost principle I'd like to convey is this idea of testing algorithms by default before implementing them in clinical workflows. And why is that important? And this is not a research paper, right? This is something that you're testing an algorithm. You are trying to know what it's good at, what it's not good at before you deploy it in clinical practice. Why is that important? Because number one, you have to build trust. Clinicians need to trust the AI. You need to answer a very, very basic question around, does it work? How much does it work? What type of cases does it work on? And maybe more importantly, what type of cases does it not work on? So the only way you can get to do that is if you build your own small data set of cases and run the algorithm on those cases and see how it performs. The next is, you could have a beautiful algorithm that performs really, really well, but is not as helpful. So the second thing pre-deployment testing helps you achieve is establish outcomes, right? Does it even help? And if it does help, how much does it help? What are clinical scenarios best suited for this particular algorithm, and what are maybe less suited? And the third is a bit of a technical, is a small technical aspect related to some of these AI algorithms, where pre-deployment testing can enable you to choose thresholds for algorithmic performance. Threshold can be thought of as the degree of suspicion that an algorithm should have for a specific finding, and how do you tweak those across algorithms? You can essentially say that if a probability is in excess of 50%, give that as a positive; if not, then negative. So this is what pre-deployment testing can help you achieve, and we'll go deeper into each of these aspects in due course. Before we dive very deep, it's important to understand what are types of AI algorithms that are there. This is the most common classification that we used, and incidentally, the first algorithm itself is a classification algorithm. So classification is when algorithm gives out a probability estimate for a specific finding or disease being present in a case, right, or in a study. So, for example, diagnosing tuberculosis on chest X-rays, diagnosing pneumonias on chest X-rays. Typically, these algorithms will say that the probability of X finding being present is 91%, and that's what makes it a classification algorithm. These are the most common type of algorithms that you will come across nowadays. The second is detection and segmentation. This is when, given a study, given a case, an algorithm first detects the presence of a particular anomaly. It localizes it, and then goes on to segment it in either 2 or 3 dimensions, depending on the type of anomaly it may be. A great example of such an algorithm is automatic calculation of ejection fraction from a cardiac MR, for example, where first, you would have to detect relevant areas of the MR and then subsequently segment out the ventricles and then calculate the ejection fraction based on that. And the third type of algorithm is a super resolution algorithm. They're also called denoising algorithms in certain cases, where you take a poor image or a bad image or a suboptimal image or a low radiation dose image or a fast MRI acquisition image, and you up resolve, or you make these not so good images into great images, right? And you use deep learning to do that. Many examples of this. There are algorithms that can take low dose CT images, make them look like conventional dose images, and the same is being done in MR and PET CT, various aspects. So as we move on, we'll start with classification algorithms. This is a framework that we propose for the testing of classification algorithms. We call it the algorithmic audit. And it starts with just helping think about what type of data is being used for evaluation. So are you using data that the algorithm was originally trained on? Like, are you using the same data for testing? In that case, you can almost always expect the model to perform really, really well. The second level of data is data from the same or similar locations as the training data, right? And this essentially means that we see several examples of papers out there where they will take let's say 10,000 X-rays and break them into train, test, and validation groups. And this is the second category where you're using not the same data, but you're using data from the same location or same hospital. Then the next step is data from a different hospital, right, or a different location. So you take your algorithm and you put it in a hospital that is right across the road, right across a continent, right across the world, right? And you see how it performs. And then lastly, which is also the most difficult and maybe not very practical, is testing algorithms on completely different acquisition parameters, right? You train an algorithm on a certain type of CT scan and you test it on a low dose CT, or you train an algorithm using T2 weighted images and you test it on T1 weighted images. So this is the general hierarchy of data, and we generally recommend that you should use data from a different location and multiple different locations in order to figure out whether your algorithm is truly working or not. The next in classification algorithms is, these are the general metrics that are used. This is a snapshot of our software called Carpal that you can use for testing of some of these algorithms. Essentially, the main metric a lot of people use is area under the ROC curve. And typically, the higher the area under the ROC curve, the better the performance of the classification model. And this is a fairly commonly used metric. The thing is that the ROC curve gives you somewhat of a mathematical intuition around the performance of an algorithm, and not really a clinical indication of the performance. So for that, we propose the charting out of such a graph where you essentially, remember, these are classification algorithms. They give out a probability estimate for the presence of a particular finding. So in this case, you take pleural effusion and you plot each of these X-rays uh, on taking on the y-axis the probability of pleural effusion being present in each of these X-rays. And once you do that, you overlay the ground truth and you get these red dots, which are true positives, where pleural effusion is indeed present in these X-rays. You get these blue dots, which are true negatives, where pleural effusion is indeed not present. Then you get these mismatches, right? These mismatches, they can be false positives, they can be false negatives, and this is your threshold line here of 30. So anything above 30 is a positive, and if it's yellow, it's a false positive, and if it's below the line, it's a false negative. And here we try to say that you should be able to look at these cases that are somewhat away from the threshold. So what does this mean? This means that in this particular case, we call it a far north failure. This particular case, the AI was very, very confident that there is indeed pleural effusion there. But in our ground truth, in our radiologist interpretation, there was no pleural effusion, and this is just an indication of that particular case. So you can, like this, you can dig deep into the performance of the AI. So the point I'm trying to make is summary statistics have a lot of merit, but there is no replacing the a deep dive into failed cases to try to figure out how the algorithm is performing from a clinical perspective. What is the nature of mistakes that it will make? Then explainability is another very important thing. It goes on to say it's essentially trying to figure out why an AI algorithm is saying what it said. And we wrote a paper on that recently, where we essentially push for this idea that medical experts, in our case radiologists, should look at the outputs of AI algorithms and try to figure out what can be done more, or what are patterns that the AI may be looking at and thereby form hypotheses around these patterns to try to figure out why the model is saying what it's saying. And this can only be done by experts. Similarly, this was a paper we wrote just recently, where we come up with this idea of a clinical explainability failure as a metric for judging, again, these classification algorithms, where essentially the idea is that it's possible that in several cases you get a true positive, right? For example, if you look at normal versus abnormal scans, and this is just an example of this, but you can see that the red boxes here are what the AI looked at in order to say that the algorithm itself um, eh, said that this is positive. And the yellow box is what the radiologist pointed out to be the abnormality in this scan. And now if you see, there is no overlap. So at an image level, it's a true positive, right? Because the AI was correct. But if you look at why the AI called it as a positive, it's wrong. So we call these explainability failures. We've gotten a lot of controversy on this paper. Happy to talk about this in the Q&A. But essentially, the idea is that is the reason the AI calling something positive the same as the reason a clinician would call something positive? And if not, you cannot trust the output. Moving very, very quickly, I know I'm out of time, to detection and segmentation algorithms. There are Jaccard index and dice scores for segmentation, where you essentially see what is the overlap between the AI output and the radiologist output. These are most commonly used. And this is an example of some of our work that we've done on prostate segmentation. But what we go ahead and then say is that while that is a great mathematical parameter, maybe sometimes we give too much importance to a dice score, and maybe we can get enough clinical information from an output that may have a low dice score, or a low performance metric, but maybe clinically sufficient. For example, here we see that this is a true diffusion image for this patient, and there is also this virtual diffusion image which is created from this same image. And if you compare the dice scores, they may not be the same of these lesions because this is significantly smaller than this, but it answers the correct clinical question, which is, does this patient have an infarct? And the answer is yes. So similarly, you can use visualization techniques to make clinical inferencing easier. For super resolution algorithms, there is always this question around, are the artifacts removed or are they hidden? Are we removing information or are we hiding information in this process? And the way we propose that can be solved is by using an approach where the same patient is scanned multiple times at different acquisition parameters with constantly deteriorating image quality to arrive at the limit of detection of the MRI for the lesion. And then this particular scan should be subjected through AI to try to figure out whether the system is truly working or not. In summary, testing of AI is literally as complex as recruiting a clinician. You need specific test sets to determine performance of specific algorithms. It is essential to deep dive into functioning of these algorithms and figure out breakpoints and communicate those with the developers. You need to validate at site and figure out if it works for you. And for deploying AI, probably a parallel IT stack would be required. So with that, I thank you for your attention and look forward to the Q&A. Thank you.